So, good evening, everyone. I welcome you all to the seventh live session of the NPTEL online course, Basic Principles and Calculations in Chemical Engineering. The course instructed by Professor S.T. Majumder from IIT Guwahati and myself, Chaitra Borkar, a Ph.D. scholar from IIT Delhi, who will be conducting this session. So, some information about these live sessions is that they are conducted every week on Tuesday from 7 to 9 p.m. The recordings of these live sessions, you can access them through my YouTube channel, and the links have been shared with you as well. The structure of these sessions is such that we'll firstly go through the overview of the lectures for the corresponding week, which is the week 7 for this time, and then solve some sample problems related to your assignment for the corresponding week. Just a minute. So yeah, let's get started. So the lecture 20 was about the mechanical energy balance. So firstly, we'll rehash the relation for the open system energy balance. So as we have previously derived this equation that the change in the rate of internal energy, change in the rate of kinetic energy, change in the rate of the potential energy plus this flow work is equal to the heat rate minus the shaft work rate. So this dot on the in the above these terms represents the rate or per time value. And if we open these each of these terms and uh, take out the common mass flow rate, so this is what we get. So if we take out common mass flow rate from here, so suppose this has units joule per second. So what we do is we convert it to mass or kg per second into joule per kg basically. All right. So this also has joule per second. So what we do here is, or you can write it as kg meter square per second square, uh, and then upon second as well. So just a minute, just a minute, just a minute. So kinetic energy is half mv square. And if we want to write it as that, so this will be m. So you can also take that that m dot out as well as common. Just a minute. All right. And then mgz again. So p will be p dot will be m dot gz. So that also gets, I mean, you can take out m dot here as well. And then p out, v new out. So new out is basically, you can write it as, just a minute. So this is basically 1 by rho. So rho is uh, m by v. Okay. So that is how you get that. And if we take m dot out as common and open these values, so u out hat. So this u hat is basically u by m. So you can write this as q dot minus you don't have to take out m dot here as common. So this is the expanded version of the open system energy balance. So for incompressible fluids, however, you can write this as delta P by rho plus U square by 2 plus G delta Z plus delta U hat minus Q by delta M. So what you do is you rearrange these terms, and when for incompressible fluids, basically rho is constant. So that is how you get this relation. And you again rearrange it in such a way. So this term here is heat due to viscous dissipation, and it basically is due to the viscosity of the fluid. So you write it as F. So for the incompressible fluids, this is the mechanical energy balance that you get. Ws dot by m dot, negative of that, is equal to delta P by rho plus delta U square by 2 plus G delta Z plus F. And from here you can derive the Bernoulli's equation, and it applies for when there is no shaft work and there is no heat due to viscous dissipation, and also for incompressible fluids. So fluids can be liquid or gas as well. So you can say that it is for incompressible fluids and potential flow. So potential flow is that one where the heat due to viscous dissipation is zero, and it is along the streamlines, as well as there is no rotational motion. So here from this term you can derive that if Ws dot is zero, so this term is zero, this term is zero, F is also zero. So this only this part, sorry, only this part remains. So you can write it here, and the change in the uh, pressure divided by density plus the change in the velocity or the kinetic energy, change in the pressure energy, change in the kinetic energy, and change in the potential energy uh, between 2 points, you can write is zero, or you can write P by rho plus U square by 2, or you can write P1 because it is at some point. GZ1 is constant basically, or you can write it in one more way, is that is equal to P2 by rho. So at some other point it will be P2 U2 square by 2 and GZ2. So the schematic is given here. So suppose there is some conduit here, and through which a fluid is flowing. So the cross section of this conduit is non-uniform. So the cross sectional area here will be smaller, and here it will be higher. So it gives us the relation of the internal. This P1 here is internal. Sorry, P1 or P2. You can say that this is internal fluid pressure. So you can say that here the cross sectional area is smaller. So you can say that if the flow rate is constant, Q dot is constant, not small q dot is constant. So Q dot is basically U into cross sectional area. So U1 is equal to A1. And if this is constant, so U1 A1 is equal to U2 A2. So if this is if this is low, A1 is low, So this needs to be higher so as to keep this term constant as well. So U1 will be if A1 small, A1 lesser. So here it is written V1, I'll write U1 is more. Okay. So and from the Bernoulli's theorem, we can also say that to compensate for this more velocity, the internal fluid pressure here will be lesser as well. Okay. So this gives us the relation between the internal fluid pressure, the velocity, as well as if there is any change in potential as well. So this Bernoulli equation is used to calculate this Bernoulli's principle is used in the several flow meters as well, uh, such as Pitot tube and others as well. So we move to lecture 21. It was about enthalpy balances without reaction. So suppose if there is no shaft work, there is no kinetic energy, no potential energy, then the energy balance equation becomes delta U dot plus delta PV dot is equal to Q dot. So all these terms, so there is no kinetic energy, no potential energy, and there is no shaft work as well. So these values get cancelled. We only get delta U dot plus delta PV dot is equal to Q dot. So that is what is written here. So you can expand delta U, you can expand this delta PV term. So and also take m dot as common. So here and you can write this term as enthalpy. So that is what is written here. And delta H cap is again H by m mass. So m dot H out cap minus H in cap is equal to Q dot. And this delta Hi can be computed using this relation. So this is standard heat of formation plus if there is any sensible heat uh, added to the system. So if suppose the temperature rises from T reference to T and this Cp is not constant for this given temperature range, there will be some relation given such as A plus Bt plus Ct plus Bt Ct square plus Bt cube. So this is some Cp given to you, and this is not constant for the given temperature range. So you basically integrate it so as to get the sensible heat. And if there is some phase change, so this is basically that term for phase change. So this is basically heat of latent heat basically. So it can be heat of vaporization, it can be heat of fusion as well. So it is at constant temperature and pressure. So from this plot, you can also see that so this from this plot you can also see that for water basically the temperature from minus 25 degrees Celsius the temperature rises. The phase is still the solid phase, and at 0 degrees Celsius and at a particular pressure. This is at a particular pressure. So 1 atm basically. So this solid converts into liquid. So there is a phase change occurring here, but at a constant temperature. And then again, so this accounts for sensible heat, this area, this accounts for the latent heat. So you can see this is heat absorbed by the sample in kilojoule. So heat is being added, however, at a constant temperature. Heat is also being added here as well. Heat is also being added here, but this is at in a temperature range. This is at a constant temperature. So this is latent heat. And then again, you increase the temperature, heat is being added to the system. So this is again sensible heat. And then at 100 degrees Celsius, again the liquid changes to the vapor phase or the steam, and you see the boiling occurring. And this is again the latent heat at a constant temperature. Again, you keep on heating the vapor, again there will be some sensible heat added to the system. So, sorry. So, enthalpy for a system without chemical reaction and no phase change would be sum of the heat of formation and the sensible heat of the constituents. So, if there is no chemical reaction and there is no phase change as well, so only the sum of the heat of the formation and the sensible heat. That's it. We move on to lecture 22 and 23. So, energy balance with multiple streams. So, different examples were taken of refrigerator, distillation column, evaporator, drying process, and the combined material and energy balance for the is required basically. So, firstly, you need to know how much the flow rate is there and how much the energy is being either extracted or is being absorbed. So I take up the example of distillation column here. So in this distillation column, basically you have a mixture of in the feed. So there is a mixture here. This can be this is a mixture basically, and you need to separate this. Suppose there are two components. It can be multiple components as well. So, I am assuming here there are two components, and based on the difference in the boiling points, one will be more volatile, one will be less volatile. So, based on the difference in the boiling point, basically you are separating these two components here. So, in this, so feed is being added to the distillation column at some point here, and this distillation column consists of different a number of trays or plates. So here you see this red arrows show the direction of the vapor, and this blue arrow show the direction of the liquid basically. So there is a mass transfer between the liquid phase and vapor phase and vice versa. So here you see that the vapor then goes to the condenser. So here we need to apply the energy balance, and again the liquid goes to the reboiler. So here we need to apply the energy balance as well. So the condenser condenses the vapor into liquid form, and here in the reflux drum we uh, we uh, we then calculate how much reflux needs to be given back to the liquid. So if there is no reflux as such, so there will be no liquid in this portion. So so as to get a better mass transfer, we reflux some of the distillate back to the distillation column, and that so this ratio is called as reflux ratio, and the distillate and the remaining amount of the condensed vapor is taken out as distillate. So and again in this reboiler, the liquid is being heated into the vapor form and given back to the uh, given given back to the given back to the distillation column, and some amount of bottoms are taken out from here. So this is how you this so basically material balance will be feed is equal to distillate plus bottoms, and the energy balance will be across the condenser and the reboiler, and the energy balance on heat of solution, the relation is given here. So again m dot delta h cap is equal to q dot. So we start with the sample problems related to your assignment 7. So question 1, which one of the following is not mechanical energy? Can anybody give me the answer for this? So the correct answer here is heat, basically. So mechanical energy can be converted into work. or heat, but it is not a form of energy. So kinetic energy is the form of mechanical energy. Potential energy is also a form of mechanical energy. Internal energy is also a form of mechanical energy. However, heat is not a form of mechanical energy. So the correct answer here is heat. Next question, the Bernoulli's equation given by this relation can be applied for fluids without viscous dissipation. Yes, correct. This is correct. Then negligible shaft work. Yes, correct. Ideal incompressible fluids. Again, correct. So all of the above is the correct option here. Next question, if the system and its surrounding are at the same temperature, or if the system is perfectly insulated, then delta Q dot is equal to infinity, or delta Q dot is less than 0, or delta Q dot is equal to 0, or none of the above. What will be the correct answer here? So there is a system T1 again T1, or if it is perfectly insulated. So the heat flow basically across the system, suppose this is a system and it is perfectly insulated. So the heat flow across the system boundary will be basically zero, because this will this is perfectly insulated, so it will not let any heat escape from the system. And also, if this temperature here in the system, temperature in the system and outside the system is same, so there will be no heat transfer basically. So there is, because there is no temperature gradient. The driving force for heat transfer is temperature gradient. So again, the heat rate will be zero across the system boundary. So the correct answer here is C part. Next question, the third term in the relation delta HI cap. So this is the relation for enthalpy. So what is this third term signify? So this is enthalpy of formation, or this is standard enthalpy of formation. This term signifies the sensible heat, and this term signifies the latent heat. We have already discussed. So the correct answer here is latent heat. Next question, if the system is not rising or falling. So rising or falling as such is related to some reference. So reference is such that there is no rise or fall. So there is no delta Z basically. So delta P comes into picture here. So G delta Z, or mg delta Z, sorry. So this delta Z is 0. So delta P will be 0. Next question. The Bernoulli's equation is derived from conservation of mass principle. Is this true or false? This is a false statement, because Bernoulli equation is derived from conservation of energy, or you can say energy balance. So this is a false statement. The unit of kinetic energy is, so kinetic energy is half mv square. So kg meter square per second square. So this is, we can write, we know Newton is kg meter per second square. Okay, so this is Newton, and one more meter will give us kg meter square per second square. So the correct answer here is the B part, Newton meter, or you can write it as joule. Next question. The region A in the given figure for the same mass flow rate has the fluid speed for incompressible fluid and negligible viscous dissipation higher than region B, equal to region B, lower than region B, or cannot say. So here you see that the mass flow rate is constant. So let's suppose area, there is some cross-sectional area A1 and some velocity U1, and here it is area A2 and some velocity U2. So A1 U1 is equal to A2 U2. I said same mass flow rate. So mass flow rate is again m dot, which is equal to density into q dot. So if density is also constant, mass flow rate is constant, so q dot will also be constant. So that is why I am saying q dot is constant. So because it is incompressible fluid, so density will remain constant. So so A1 is less. Oh, sorry, A1 is higher than A2. So to keep this relation constant, U1 will be less than U2. So U at point A will be less than U at point B. So what that is what we need to find out. Has the fluid speed in region A fluid speed will be lower than region B. The correct option is C part. Next question. The region A in the given figure for the same mass flow rate has the internal fluid pressure for incompressible fluid and negligible viscous dissipation higher than region B, equal to region B, lower than region B, or cannot say. So here we will apply Bernoulli's theorem. So P1 by rho plus U1 square by 2, and because there is no you can say from the reference, suppose here the center of this both the Z1 is equal to Z2. So you can say delta Z is 0. So potential energy term will be 0 here, is equal to P2 by rho plus U2 square by 2. So from the previous question, we found that U1 is less than 2. So to compensate, to keep these terms constant, so if U1 is less than U2, the internal fluid pressure I'm talking about will be greater than P2. So it will be, or you can say PA is greater than PB. So higher than region 1. Next question. An airplane flies through the sky where the air flows horizontally above over the airplane wing at a speed of 130 meter per second on the top and 100 meter per second on the bottom of the wing. The air density is 1.2 kg per meter cube and the wing is 8 meter long and the average width is 3 meter. What is the pressure difference on the two sides of the wings? So here we will apply the Bernoulli theorem as well. So delta P by rho plus delta U square by 2 plus G delta Z is equal to 0. So basically this is the, suppose, the airplane wing, and some velocity of air, this has U1, the above the wing the velocity is 130 meter per second and U2 is 100 meter per second and the average width is given 3 meter. So this 3 meter is quite negligible, so you can basically neglect it, keep it as 0. So the only term remaining is delta P by rho plus delta U square by 2 is equal to 0. So delta P by 1.2, sorry, So we need to find out basically the delta P. So delta P and delta P will be P2 minus P1. Okay. So 1.1 by 1.2, which is the air density, 1.2 kg per meter cube. All in SI units are here, so I'm using the same value. The and delta U will be sorry, delta U square will be U2 square minus U1 square. So that will be 130 square minus 100 square divided by 2 is equal to 0. So if you solve this, this comes out to be so 130 square minus 100 square, it is 6900 by 2, and if you multiply 1.2, this comes out to be 41. So delta P comes out to be 4140 Pascal. The correct answer is B part. Next question. A cylinder fitted with a movable piston is filled with gas. Is filled with gas. The amount of 20 kilojoule of heat is transferred to gas to raise the temperature by 150 degrees Celsius. So some heat is being added, and the gas does 40 joule of work in the moving piston to its new equilibrium position. So some work will be done by this gas on this piston. So work done. Um, and what should be the change in the internal energy? So basically, heat is being provided to this gas, and these atoms are then get atoms in the gas that get excited, and because of that, it will do some work on the piston and to reach its new equilibrium position. So what should be the internal energy of the system? So there is no mention of the kinetic energy, no mention of the potential energy, there is no mention of the PV work. So basically, we get the relation as delta is U is equal to Q minus W. So we know Q, we know W, we can find out delta U or the change in internal energy. So keep in mind the units. This is 20 kilojoule minus, you can write 0.04 kilojoule. So 40 joule will be 40 by 1000. So this will be 0.4 kilojoule. 0.04 kilojoule. So the correct answer will be 20 minus 0.04 will be 19.96 kilojoule. The correct answer here is C part. Next question. Distillation is a process in which condensation takes place, evaporation takes place, simultaneous evaporation and condensation takes place, or none of the above. What will be the correct answer here? What will be the correct answer here? Mayuri, can you see my slides? Hello? Mayuri, can you see my slides? Okay. So, can you answer? Distillation is a process in which condensation takes place, evaporation takes place, simultaneous evaporation and condensation takes place, or none of the above? Can you give me the answer for this? So, I'll just show this GIF. So, basically, feed is being transferred. This liquid goes to the bottom, passes through the reboiler, vapor comes in. So, and this vapor goes to the condenser, and again, liquid is being given back as reflux ratio. So, both condensation as well as evaporation takes place. The correct option is C part. Next question. A binary distillation column separates 200 mole per hour of a feed mixture into distillate D and residue W. Calculate the distillate and residue flow rate in mole per hour. Given XF or the so this XF is basically mole fraction of volatile component. Volatile component will come out from the majority of volatile component will come out through the distillate. So mole fraction of volatile component. All these are the mole fraction of the volatile component. XF. So XF will be mole fraction in feed. XD is mole fraction in distillate of the more volatile component itself. And XW will be in residue or bottoms. So you see this 0.96 mole fraction. So the more volatile component is enriched in the distillate, and it is in rarer quantity in the bottoms. So here we draw a schematic. So D, this will be W, this will be F. So from the so we will basically have to do the material balance. So firstly we'll do the overall material balance. So F is equal to D plus W, and then we go for the component material balance. So this will be F, this will have XF, this will sorry, this will be XD, and this will be XW. So this is for just one. This is the more volatile. This is for the more volatile component. If again there will be some XF for the XF2, you can write XF1, XD1, XW1, and XW2. So we are basically given XF1, XD1, and XW1. Okay, so we can write the component material balance F into XF1 is equal to D into XD1, W into XW1. So we don't know D and W, we need to find that. So F we know. So the two equations will come out to be D plus W is equal to 200, and then 200 into X of 1 will be, so this is 200 into 0.5. So this will be again 100, and then D into XD1. So XD1 is given as 0.96, and x w1 is given as point sorry 0.02 w. So these are the two equations to be solved. So there are two unknowns, d and w, and two equations. So we can solve this. Um, the correct answer will come out to be, so basically what you can do is multiply this equation by 0.02. So if you multiply that, so this w and w will get cancelled. 200 into 2 by 100 will be, so 100 cancelled. So this will come out to be 4. So and you then subtract this. So 0.96 sorry 0.96 minus 0.02 d is equal to 100 minus 4, so that will be 96. So 0.96 minus 0.02 is basically 0.94 d is equal to 96. So you can compute that. So d comes out to be 102.13 basically. So d is 102 sorry 13 mole per hour. And then you can compute W as well. So W will be from this equation itself. W will be F minus D. That comes out to be 97.87 mole per hour. So correct answer is D part. Next question. For a distillation column, the operating line for rectification is always below the equilibrium curve, above the equilibrium curve, cannot say. So the correct answer here is below the equilibrium curve. You cannot have any operation in distillation column, whether it is rectification or stripping, to be above the equilibrium curve, because that is the maximum mass transfer that you can do. So from either the liquid to vapor or vapor to liquid, both the operating line will be below the equilibrium curve. Here is a schematic that I show here. So this is basically how you compute the number of stages in a distillation column. This is called the NOC25 plot. So basically you have the plot of vapor mole fraction to the liquid mole fraction. This is for the more volatile component. So there are two components basically, one is more volatile, one is less volatile. So this is for the more volatile component. And then you get the equilibrium, this is the given data. So this is the equilibrium curve, this red curve here. And you operate basically below this equilibrium curve itself. So this is the operating line for rectification, and this is for this line, this is for stripping, and this is the feed line, and it depends on the type of feed that you are putting in. Either it is saturated liquid, saturated vapor, superheated liquid, superheated vapor, or a mixture of it. The slope of this feed line changes. So and when you draw these operating line as well as the feed line, the intersection of this, so from this point, so you know the composition of the distillate basically. So from here you start from the so you go from this is 0.85, so from 0.85 you start, and then you draw the straight line towards the equilibrium curve, and then go down towards the operating line for the rectification. And again you go from this point, you draw a straight line towards the equilibrium curve, and then go down, if you reach the stripping curve, so this will be the reference for you. And again, so number of these triangles that you get, are basically the number of steps. So, so that is how you get your number of trays basically for the number of trays or number of plates for and these are theoretical plates. So which assume that the liquid phase and the vapor phase are in equilibrium. So that is how you get that. And we move. So the correct answer here is the distillation column. The operating line for the rectification is always below the equilibrium curve. Next question, at total reflux. So reflux is basically this is some liquid being given back to the distillation column, and this is the distillate. So reflux ratio is basically L by D. So at total reflux, so basically you are not giving any distillate out. So reflux is basically infinity because distillate is zero. So distillate is nil, P part. And then reflux will be reflux ratio will be basically infinity. Next question. If a distillation column is operated at total reflux, maximum number of stages are used. So we go back to this diagram here. So if the total reflux is being used, so this operating line of the rectification basically changes. So the slope actually becomes equal to this xy line. This xy line is at 45 degrees. So basically what you get is, suppose this is the equilibrium curve, this is the plot of, sorry, I'll draw a better one. So suppose this is the xd. So suppose this is the operating line for some reflux ratio. When you keep on increasing the reflux ratio, this slope keeps on decreasing because it depends on this intercept. So intercept is basically xd by r plus 1. So if you keep on increasing this, the intercept, this is basically the intercept. So intercept will keep on decreasing. So the slope also keeps on decreasing. And you basically get the slope is equal to the xy line, which is the 45-degree line here. So at this point, x is equal to y. And because of that, the number of steps will be, so we remove this line. Oh, sorry. Uh, so basically, the operating line for rectification will be this xy line itself. Operating line for stripping will be xy line itself. So you start from this xd, and this will be xw. So you reach here. And in this case, the number of steps will be, or the number of trays will be minimum. Because if you have some reflux ratio, um, not total reflux ratio, some optimal reflux ratio. So you get this some operating curve. This will be the feed line. So from if you start from here, if you again go there, the number of steps keep on increasing. So and if you keep on decreasing this r, decreasing this r, you will get to the point of minimum reflux ratio. And at that point, the number of theoretical plates will be infinity. So the correct answer here is, if a distillation column is operated at total reflux, maximum number of stages are used. This is a false statement. It should be actually, so at R is equal to infinity, I can write here, sorry, at R is equal to infinity, uh, I can write the number of plates is equal to minimum at R is R min or minimum reflux ratio. It cannot be zero. R min, it will be sorry, it will be the NP will tend to infinity. So the correct answer, this is a false statement. Any questions in this regard? In this for this week 7, any questions? So if there are no further questions, I'll go ahead and close this session for today. Thank you everybody for joining.